this is the last day that is not just math. So after today, we're going to introduce solution stoichiometry. We talked about it the first day. It's manageable, but we have a lot of chemistry first that we've done. That's going to apply now to math. Like it all comes together like the 18. So here we go. Objective, learn about and be able to write and balance simple redox reactions. And I mean like super simple, because these are extremely complicated, but in chapter 4, they're not. They're, well, Preston, that's not cool, red eyes. We will get much more complicated ones when we get to chapter 19. All right, next we're going to learn about and apply the activity series. The activity series is a table that shows you like how reactive something is based on how easily it is oxidized or reduced. All right, so what success looks like today, it looks like this. Now, this is not really done, but you'll have a question here. It will say, which of the following reactions will not happen as written and why? Now, look at the screen for a minute. These have nothing to do with solubility rules. Oxidation and precipitate chemistry is different. They don't relate to each other. Okay, so it's kind of tricky. It's like for 2 weeks, I've taught you how to play soccer, and then we're playing baseball, and you think you can't touch the baseball with your hands because you couldn't in the other sport, right? Well, it's a different thing with different rules. So here we go. Oxidation and reduction. Now, the thing I handed to you, it will be important. It will just be our practice thing with our rules. So what we have here is we'll typically have a single element, some sort of compound, or another single element, I guess it doesn't really matter, and they exchange electrons between each other. When there's an exchange in electrons, it is called an oxidation or reduction reaction, or both we call a redox reaction. So an oxidation occurs when an atom or ion loses electrons. Nice. All right. A reduction occurs when an atom or ion gains electrons. I will tell you right now, we're already into where most of you get lost. Wow. So please trust that you can be reduced by gaining. You can be reduced by gaining, and oxidation is when you lose. How are we being reduced when we're gaining something? Any ideas? It lowers the charge because the thing we're gaining is an electron, right? So if you have more electrons, you have more negative charge, or you've been reduced. All right. I'm going to teach you 2 sayings. You're welcome to ignore both, make fun of both, like one, hate the other. I don't care. But there are 2 sayings, if you'll memorize, they will help. The first one is, oops, right here. Leo the lion says grr. Leo the lion says grr. All right, if Peter Burt was in here, he'd really say grr. I don't have that personality. No. So here's what they mean. If you look, Leo is LEO, which means if you lose electrons, you're oxidized. Leo, lose electrons, oxidized. All right, so Leo the lion says grr. That's about as good as you're going to get from Mr. Davidson. All right, Leo, lose electrons, oxidize. Tell your partner what you think GER is. Reduced, you mean?
Yeah.
Okay. If you gain an electron, you're reduced. So lose electrons, oxidize, gain electrons, reduced. Bert did say I look smarter with these, so maybe you'll trust me more. Does that help? GER. Reduced. Okay, the other way to memorize it is oil rig. That one's been a little more popular since it hit YouTube. Oil rig. Oxidation loses. Reduction gains. Sorry. I will write red a lot. And then you can see my picture of a lion and my oil rig from 2 years ago. Yeah, clearly a lion. It looks like Mr. Bert's costume is what it looks like. Why is there what? I don't know. I'm really not an artist. I'm married to a great artist, by the way. 30-second timeout. Are you ready? Hold on, let me. I don't know. Yeah, so I can show you like the artwork my wife did.
Oh my gosh.
So that's her pumpkin she did yesterday.
That is amazing.
Yeah, so I don't need to do art. We used to have a church activity when we all sat together on the same bench where my kids, they would ask me and my wife to draw something and then they would laugh. Yeah, I will tell you the only thing I'm better at drawing than my wife is a tank. I am really good at drawing tanks. Nope, because I really suck at it now. Anyway, that's my wife. She teaches music at Foothill. Yep. Starts like this. Get your track right here. Oh, it's so hard to draw on this slate, but just trust me, I was good at drawing tanks. Okay, not oil rigs. Are we all right so far? Okay, next. All right, so you need to understand the following. Oxidation cannot happen without reduction and vice versa. Because you can't gain an electron unless something lost it, because electrons don't just spontaneously exist. They had to have come from somewhere. So I got a question that goes way back. In a reaction, who do you think could give an electron away? A metal, because metals are losers. So who's going to take it? Non-metals. So yeah, like oxygen. And that's why it was originally called oxidation. They didn't realize what it had to do with electrons. They just knew things reacted with oxygen like iron and would rust or oxidize. So, all right. So we have to have both. Substance oxidized loses, and then reduced gains. This is the ghost running the mile out in PE, so it was distracting. Okay. To determine if an oxidation reduction reaction has occurred, we assign an oxidation number to each element in a neutral compound or charged entity. Okay, I think we're ready for this side here. Oh, whoa. What magic just happened? What are the odds of that? Okay, so turn to the side that says oxidation numbers. You with me? If you're over there and you have no idea what happened, I dropped the paper and it curved and it caught between the metal of the desk and the desk.
Both sides say oxidation number.
Sorry. That's funny. This one.
What's the first one on?
It says print off this and the next page. Sorry. All right, here we go. Let me see, I have this here. Please focus on this because it's not hard compared to a lot of things we've done. But if you don't stick with me, you're lost, and then it's as hard as anything we've done. Okay, first off, an oxidation number is very similar to the substance charge. So like when we've said Na was a +1, its oxidation number is a 1. Now, the difference is they're not always the exact same. Like chlorine is a -1, unless it isn't. We'll learn how. But they're similar to their charges. So there's only this many rules. All right, here we go. An oxidation. So we are going to assign oxidation numbers based on these rules. So elements in their elemental form have an oxidation number of 0, which we've sort of said. We said an element by definition is neutral. The ion is not, but an element is neutral or it has a 0. We'll come back to all this in a second, or sorry, we'll go to the other side and practice in a second. The oxidation number of a monatomic ion is the same as its charge. So if it's Na, well, that's a +1. If it's Cl, it's a -1. If it's monatomic, tell your partner what monatomic means. It means one atom, right? Or another way to say it, it means not a polyatomic ion, because that's when the fit hits the shan. Go. No, they're right. Na lost. It lost a negative, so it became positive. It gained, Cl gains a negative, so it becomes negative. Okay, ready? Next. Nonmetals tend to have negative oxidation numbers, although some are positive in certain compounds or ions. We will have some very positive nonmetals today, but that's because they're going to be with something else that is bigger and badder than they are. Moving on. Oxygen. This rule right here and this rule right here, they get us like 80% of the way through every problem. So make sure you know these. Oxygen has an oxidation number of -2, except in peroxide, in which it has an oxidation number of -1. You hardly ever deal with a peroxide. So tell your partner right now, oxygen is pretty much always a -2. It's always a -2. Okay. Next, hydrogen is a -1 when bonded to a metal and a positive when it's bonded to a non-metal. It's a little weird. It can be either way, because if you think about it, hydrogen had one valence electron to lose or gain, right? So it could become positive or negative. Fluorine always has an oxidation number of -1. Do you see any exception on fluorine? All right, based on some things we've said before, which really most of it's coming in a different chapter, but maybe tell your partner why fluorine has no exceptions. We haven't really dove into this yet. Divin? Anyone have any idea why fluorine is the boss? No, it's because it's a jerk. Fluorine, we'll learn about this in a later chapter, is the most electronegative atom. It's the best. You did? Who said that? Nice. It's the best atom at stealing electrons of all of them. Now, we have a new name today for stealing electrons. Tell your partner what it is. All right. It oxidizes, or it makes something lose electrons. All right. Fluorine wins every fight. When you have Bert, electronegativity is the hotness factor. Fluorine is the man that can steal your girl, no matter what. Like, I don't care who you are, fluorine's going to win. Fluorine's going to win. All right. Okay, here we go. The other halogens have an oxidation of -1 when they are negative. They can have positive oxidations, however, most notably with oxy and ions. Okay. We just learned fluorine wins all fights, all of them. Based on this sentence, who wins every other fight? Like it so far. No, closer. Nope. Nope. I heard it. I don't know who though. Nope. Are you saying oxygen? Oxygen. Oh, I said I heard it, but I didn't know who. All right. Oxygen. Look, this is how we know oxygen's the second biggest bad A. Fluorine, no exceptions. Family 7, yeah, they're pretty cool unless they're with who? Oxy and ions or oxygen. So oxygen, which is way more plentiful, it wins every single fight except for if it fought fluorine, but that doesn't really happen that often. Okay, so it will just, fluorine will take the electrons from oxygen. It's not like a big deal. We call it oof. I just made that up. I thought that was gold. My 7th grade son would be lying or just dying on the floor laughing is what I'm trying to say. I was able to fit oof into a conversation. Okay, here we go. Let's apply. Why was there a picture taken of me right there?
We think you look like the exact words.
No, that is to me, it's like the worst movie ever created. Who hates that movie? Anyone? It's like 3 hours of torture for no reason. Yeah. Okay. Let me put my super fancy, whatever these are on again, glasses. All right, are we ready? Next page, turn it over. Now, I guess it's annoying how I printed it. You might have to flip back and forth a lot. I used to print them on the same page, but they're just so small. So I went inconvenience, but bigger. Are we ready? So what we have a reaction here. Ignore that one. Where iron chloride reacts with zinc to make zinc chloride plus iron 3, I apologize, plus iron. Okay, now this reaction is different than anything we've done so far this chapter. How is it different? They don't do the switcheroo-ish. There's only 1, 2, 3, 1, 2, 3 on both sides, right? Instead of 4. So instead of, it's easy in relationship. Our double replacements instead of 2 couples just switching. Now, if like a couple of you will remember, we now have Tom and Shannon on a date. Remember Tom and Shannon? Saddest day of my life. All right. That was my girlfriend when I was a sophomore. Then I went on a trip for Christmas break and my friend Andy moved in. And then I came home from my trip and guess what? It was now Andy and Shannon. Yeah, there's a way. And then Tom. So it's very simple. You have 2 things together and a loner, and then the loner kicks one of them out, and you now have a different compound and a new loner. These are called single replacement reactions. Single replacement reactions. Okay? They're also called redox reactions. A single replacement reaction will always be a redox reaction. Turn and tell your partner the sentence I just said. You can eat first. Okay, you're good. Okay, so a single replacement will always be a redox. Now you don't have to write why, but the reason why is because there's always changes in charges. So let's apply our rules and see what we got going here. So I'm going to erase Tom, Andy, and Shannon. All right. And we'll just move on. I did. It only took me 30 years. Actually, 30 years to be right. Like right now, like literally. I'll turn 46 on November 13th. I don't know if you guys knew my birthday was that day. Okay. November 13th. Okay, here we go. We ready? Right here. Zinc and iron have nothing with them, so they're just elements. Thumbs up. You okay with that? Okay. So what would their oxidation numbers? Don't tell me. Tell your partner what the oxidation numbers. 0. How come? Because I told you so. Rule number 1: in their elemental form, their oxidation number is 0. Whoops. So I'm going to put a little 0 above zinc and a little 0 above iron. Now looking right here, look at me. Zinc was alone, but now it's with someone, right? You change. Oh, you change. Trust me. All right, it's for the good. At least that's what I tell myself. Okay. If it's with something, it's no longer a 0. So here we go. Now we just use what we know. Iron is a transition metal. How do I know its charge? All right, the number of chlorines, right? It's a +3. Is everyone okay with that? Like that goes way, way back, but I have concerns. A lot of you have no idea what I just did. Okay, chlorine is a monatomic ion right here, right? So its oxidation number is the same as its charge. It's in family 7, so its charge is a -1. Fair enough? Okay, coming over here. Zinc is one of those metals we had to memorize. Anyone have that stone cold? 2. You could also tell it because of the 2 chlorines, right? It's a +2. Chlorine is still a -1. All right. So we've assigned their oxidation numbers. Have any of them changed? Yeah. So we have a redox reaction. You have to do more things for a redox reaction. When you do these problems, you have to identify which element is reduced and which one is oxidized. So what you do is you draw a bracket between zinc and zinc +2. And then you draw a bracket between iron and iron +3. Okay, zinc's close to itself right here, so I'll start with that. Zinc went from a 0 to a +2. Short conversation with your partners. Does that mean it lost or it gained? Ready, go. Wow, my watch is going ham. All right, so here we go. From walking from there to about where my birthday sign was, I heard the word gained most of the time. But by the time I got over here, I heard oh wait, and then I heard os. So what do we think? Gained? Anyone still? It lost, right? And I know you're like, oh, this sucks. How is it a positive? Because the thing we're exchanging is a negative. So zinc lost how many electrons? All right, so lost 2 electrons. And then I'm going to say that that means it is oxidized. So I have identified that zinc was oxidized and it lost 2 electrons. Now, I did hear someone say it lost because metals are losers. Well, that's true, but who got reduced? Iron, and it's the metal. So yeah, life's crazy. All right, so iron went from a +3 to a 0. So what happened to it? All right, it gained 3 electrons, and so it was reduced. Now, any self-respecting AP chemistry student should realize we got a problem. Anyone know what the problem is? The charges aren't the same. They have to be the same. But we haven't done what yet? We never balanced it. So if we do balance it, well, you try and balance it real quick. Then I'll do it for you, and then we'll see what happens. All right, so raise your hands if you have it balanced now. Okay, let's look at it. What do you do if you see a 3 and a 2? Swaparoo. So the 3 goes here, the 2 goes here. And do I need to finish anything else? Yeah, I just put 2 iron, so I better put a 2 here. And I better put a 3 here, right? Okay, please just watch and listen for a second. Iron gained, oh, that's a terrible combination. It's just terrible all over the place, whatever. Well, I give up. But iron, look right here. Iron gained 3 electrons, right? But it did it how many times? Twice. So if 2 of them gain 3, how many total? 6. Okay. Zinc lost 2, but how many times? 3. 3 times 2? 6. If I lost and gained the same amount, then I have 99% chance I balanced the reaction correctly. The charges must balance. Okay, on the exam, you have to do all of this. If it's an oxidation reduction reaction, you have to balance it. You have to identify who's oxidized, who's reduced, and the number of electrons that were lost or gained. Fair enough. Okay, let's look at this one. Who likes to save time in their life? Okay, good. My number 1 advice to you then is to learn how to watch YouTube videos at 2 times speed and listen to a book at 2.5. Then you get a lot of time back. Okay, but my next piece of advice is right here. Look, we're looking for things that change. You with me? Things that change. In order to change, they would be with different things. So you are welcome to find the oxidation number of this O and that N and that O and that N, but NO3 is together on both sides, right? So is it changing? No. We'll find our oxidation and reduction things other places than if a polyatomic ion stays together on both sides there. Now, for now, I'm going to find the oxidation numbers anyway, but you don't have to. So here we go. Sodium monatomic, I'm ready to roll, +1. Hydroxide, ooh. All right, we have oxygen. It's a -2. Always, unless it's with what? Nope. Nope. Peroxide, unless it's with itself. All right. Now, if you look, that would mean hydrogen must be a positive, nope, 1. Because if you remember, OH equals a -1, correct? Okay, and look, this stuff right here all has to add to 0. If it didn't, NaOH would have had like a plus charge or something like that, but it did not. Okay, so far, are we okay with NaO and H? Okay, I'm just going to go ahead and put all the O's are -2. You with me so far? I can also put this H as a +1. With me? Okay. All right, then I'm mostly there. What is Ag? +1. +1. Silver's a metal. You got to memorize. All right. What's Na over here? +1, right? Okay, my friends, let's talk about N in NO3. N should be -3, but it's not. It's not, because it's in a polyatomic ion, and specifically it's in an oxyanion. Follow me here. NO3 has an overall charge of what? -1. Is everyone okay with that? Now, if you haven't memorized it, goodness, you need to. Okay, now follow me here. Oxygen is a -2, correct? Okay, you're super close, but way off. You'll see why. Ainsley says we need a +1, so it adds to -1. That is super true, except for there's 3 oxygens. Okay, so watch here. To find nitrogen, nope. What's 3 times -2? What number -6 equals -1? So +5. Which is the same idea you said. You just had to triple the whatever. Because oxygen is more electronegative and can remove its electrons. Oxygen's the boss. It tells everyone to do except fluorine. Okay, so it's like, I don't know, maybe this is offensive, but oxygen's like the dad. Lays down all the rules, but really, who's in charge? The mom. And that's fluorine. Okay, that's how it is in my house. Now, I'm not scared. I'm not going to finish that sentence. Just kidding. She's amazing. But, yep. Okay, will you right now look at this and identify the things that change? Tell your partner what changed. Which atoms changed charge? Ain't none of them changing charges, right? So I have a question, and I didn't screw up, by the way. This is on purpose. Is this a redox reaction? No, it's a what? Double replacement, or starts with a P. Precipitate reaction. It's a precipitate reaction. Now, is that a dirty trick? Sure. But on the test, you're just going to have a list of reactions, and you got to do all these things. Some of them will be redox reactions. Some of them, none of their charges change. So this is not a redox reaction. It is a net ionic precipitate forming where you have Ag plus OH minus goes to solid AgOH. You don't have to do any oxidation crap. So look, and I have a little like flow chart broken down for you. We'll see if we get there today. We probably will. You would have already done a precipitate reaction here, like if you go in order before you got to there. So not a redox reaction. Okay, here we go. Number 3. We have NH4OH plus HBr goes to H2O plus NH4Br. If you were forced right now to guess if it's a redox reaction or a different style, what would you say? It's probably a You're super close. Close. It's a neutralization reaction, which you were all there. You were saying the acid one or the base one or the whatever. But what did it make? Water and a salt, right? Okay. So I'm not going to bother writing out the oxidation stuff for this. Are you okay with that? I see an acid. I see a base. That should be like right here, like, oh, if I see H plus and OH minus, I probably have a net ionic where I form water. And then I'd have to check, is it weak or strong? There is a strong acid and a weak base. My head kind of got backwards in my head. So it'd be weird, but whatever. Okay, number 4. Looking at number 4. Where is number 4? Okay, it is on that one. I don't know what I just made bigger, but it's going away. Okay, that was weird. Okay, number 4. Looking at it, what do you think it is? It's a redox reaction, because earlier, somewhere maybe you wrote a sentence that said a single replacement is always a redox reaction. Now, what do I mean by single replacement? Oh, wait, there isn't even one of these. That's okay. We can rewrite our sentence. I apologize. If we have a lone element, which in a single replacement, we have a lone element, right? We're going to have a redox reaction. Because think about it. And I know this is new, so it might be hard to like, what? But this is going to be a 0, right? When it's alone, it's 0. When it's with something, it's not 0. So did a charge change? Yes. So it has to be a redox reaction. Okay, here we go. So I'm going to find oxygen. When it's an element, it's 0, but over here it is a what? -2. Okay. Will you see if your partner is awake, and then see if they know what the charge of chlorine is? On the left, what's the charge of chlorine in KClO3? It's hard. It's not on the board. How are you? Good. Got a bad combination. Someone asleep and someone that came in way late. All right, here we go. Show me how many fingers, what its charge is. Oh, I got some shifting numbers here. It is a +5 on the left. I'll let you be all right, because all of you that held up one finger, you were talking about the right side, right?
Yeah.
Yeah. Okay, so it's a -1 here, but KClO3, it is a +5. Please be honest. Who needs me to re-explain why it's a +5? Okay, that's enough sample size that we should do it. I have KClO3. I know this is a -2. I know K is a monatomic ion, so it's the same as its charge, which is a +1. But remember, all this has to add to 0. And this is a -6. This is a +1. So we have +1 something -6 equals 0. So what does it have to be? Has to be a +5. All right. Now, like that's the same as N was in NO3. Yeah, it's because N was with 3 oxygens and chlorine is with 3 oxygens.
So there's 3 oxygens.
Weird.
+5. If it's with an element.
Pretty much. All right, even if it's not. Okay, so here we go. We have +5 with chlorine, potassium +1, potassium +1. Now you would look at it, did anything change charge? The K and the Cl. If you do this and you only identify one change, you're wrong. Because remember, we have to have both oxidation and reduction. So we do have two things that have changed. Did I say the K? Not the K, the O. The O. It's okay. I agreed with you, so it's my fault. The O and the Cl. Are we okay with that? Okay. Would you, on your own for a second, or with your partner if you still need help, identify who was oxidized, who was reduced?
I think that's wrong.
You think what's wrong?
How do you know that? How do you know if it was a redox? Because Lisa.
All right, here we go. So my friends, we have oxygen from a -2 to a 0. You with me? If it was negative and it went to 0, what happened to it? It lost how many? 2 electrons, which means it was oxidized. Now, I have a question. Does oxygen want to lose? No. So, in case you wondered, that reaction requires energy to happen. Naturally, this reaction would go the other direction because oxygen wants to gain. All right, here we go. Oh, that hurt. Oh, okay. Chlorine went from +5 to a -1. So it definitely became more negative, right? So it gained electrons. How many of them? 6. Because it went from a 5 to a -1. And so it was reduced. Now that doesn't seem to work. Are they balanced? All right, well, we could balance it. What do we got to do? Better put a 3 here. Better put a 2 here. Better put a 2 here. All right. Okay, now this will confuse some people. It's okay though, because you don't really have to do this. Chlorine gained 6 how many times? Twice. So that's 12, correct? Now watch how this works. 3 oxygens lost 2 times. What's 3 times 2 times 2? 12. Okay, so when you try and make sure they balance, you have to include the subscript for how many of them did it and the coefficient for how many times that many of them did it. Might be tricky, but we got it. Hold on. All right, here we go. Number 5. What do you think here? What type of reaction is number 5? It is a combustion and it's a redox. Everybody, every combustion reaction is a redox reaction. But let's go back to what we said a second ago. What was the way I reformed the statement? Anyone remember? Okay, if it has an element by itself, it will always be a redox reaction. always be. Even though this is combustion, it's still a redox. Every combustion will, because it always has a lone element. It always has an exchange in electrons. Okay, will you try number 5 on your own? Number 5 on your own. Like the redox part, what we've been doing today. I'll pause for a minute. Times of me running out of time. I'm going to start. Okay. Oh, extend page. Come on. There we go. Here we go. Number 5, CH4 plus O2. I'll do the easy ones. O's a 0 here. O's a -2 here. O's a -2 here. Correct? All right. H is with a non-metal, so it's a +1. But there's 4 positive ones. So carbon here must be a -4. Are we okay so far? Okay, over here, there's 2 -2s. So carbon is now a +4. Hydrogen still a +1 here. Okay, so who changed? Carbon definitely changed a lot, right? And oxygen changed in a couple places. Okay, so carbon went from a negative to a positive, so it definitely what? Definitely lost. It lost 8 electrons, in fact. Oxygen oxidized it. So this, as written, this is the way nature would do this. This is what heated the water that you took a bath or shower in today. This reaction, unless you have propane at your house. Okay, oxygen went from a 0 to a -2. Is that what it would want to do? Yeah, it wants to gain. So it gained. That's too much attitude, huh? Oh. Oh, I know it's confusing. Promise me. I struggle with this my whole life.
Wait, so do you not put the 2 -2s together?
What do you mean?
Like, would it be 4 electrons?
There will be, it happens a bunch of times, but you would only write 2 here because an oxygen didn't change 4. It changed 2 times. Does that make any sense? Okay, then we must be out of time. You're packing up. Then we would balance this. This is 1, 2, 1, 2, if I remember right. Okay, then we'd have to do all sorts of stuff, but it's not hard. It gained 2 times twice. 2 times 2 times 2 is 8. It lost 8 one time. Okay, real quick, number 6. Is it an oxidation? I'll be super proud. What is 6? It's a gas forming red flag.
How do you know that stuff?
He has a good memory.
Yeah, we know.
We see sulfide, it makes hydrogen sulfide gas and a salt. All right, love you guys. Have a good weekend. Be safe.
I'm actually struggling so bad. I hope my